Hello children, how are you all? Hope you all are doing well. Welcome to Electron Chemistry Center. This is VKM. Children, if you like the video, please like it. And moreover, most of the students and most of the people are watching the videos without subscribing it. Please subscribe to the channel. That would be a great support to me to do more and more videos because a subscription costs nothing. The same, chemistry lectures, if you just go outside you have to pay a lot. I am providing free content and free lecture videos of all the chapters. I'll be trying to make all the chapters lectures videos which are good enough to prepare both JEE and NEET as well as CET of any state. So please encourage me by subscribing to our channel as well as please share the video to as many as you can. That will be definitely helpful to me. Let us start the lecture. In this video, we will be continuing the states of matter. We will be continuing the states of matter. We will be continuing states of matter. Already in the previous lecture, we are done with gas laws as well as Graham's law of diffusion, Dalton's law of partial pressure. All those topics are done. Now we are doing with kinetic molecular theory of gases. Kinetic molecular theory of gases. For sake of convenience, we call it as KTG. KTG is nothing but kinetic molecular theory of gases. And what are the postulates? What are the postulates in KTG? In kinetic molecular theory of gases, what are the postulates involved in it? Let's make a look on it. Yeah, just hold on. Yeah, let us continue. Just I gave a middle break. Postulates of the KTG, that is, gases are made up of gases are made up of small structural units. Small structural units called as atoms or molecules. Atoms are molecules. Whatever the system we are going to consider, that system might be a container or a vessel which is filled up with gas. Entire gaseous system is made up of small structural units. Those structural units are called as atoms or molecules. And as well as these gas molecules can move randomly, in all directions. Can move randomly in all directions. Gaseous particles, as you know that whenever when we take these gas molecules in a vessel or a container, they can move randomly in all directions, but they can move in straight line. The movement of the gases can move only in straight line. Gases can move only in straight line. They can only move in a straight line. Okay, that is another postulate. Of course, kinetic molecular theory of gases is very important question also for many of the board examinations. When these gas molecules are moving in the container or vessel, they can collide among themselves as well as they can give the collisions with the walls of the container. So gases can collide among themselves. Gases can collide among themselves and with the walls of container. And with the walls of container, with walls of container. And moreover, all collisions are perfectly elastic. All collisions are perfectly elastic. So what does it mean? All collisions are perfectly elastic in the sense that is total energy remains conserved. Total energy remains conserved. That means the energy of the whole gaseous system remains constant. Let us say one gas molecule hits with another gas molecule, and this gas molecule transforms its energy to the another gas molecule. In the same way, this gas molecule transforms the energy into the another gas molecule. It goes on. Many gas molecules, they can transform their energy whenever they are colliding with other gas molecules. But the overall energy remains conserved. Overall energy of the system, gaseous system, remains constant. There is no loss of the energy during the collisions. That is called all collisions are perfectly elastic. Okay. And there is no intermolecular attractions. There is no intermolecular attractions. There is no intermolecular attractions between gas molecules. Between gas molecules, you cannot find any kind of intermolecular attractions. Gases cannot attract and neither attractions nor repulsions. Okay. And moreover, the pressure exerted by the gas pressure exerted by the gas is directly proportional to number of collisions per unit area per unit area per unit time per unit area per unit time. So whenever these gas molecules are colliding among themselves, as well as when they are colliding with the walls of container, by that what will happen? Pressure developed due to the collisions. So more the number of collisions, more will be the pressure exerted by the system. So pressure is directly proportional to number of collisions which are taking place by the gas molecules. That is also another postulate can be taken. Another one, volume of gas molecule, volume of gas molecule is negligible, is negligible when compared to is negligible when compared to volume of gas is negligible when compared to volume of gas. See here, volume of the gas in the sense that volume of the container, because gases can take the shape of that container, right? And moreover, the volume of the container is equal to volume of the gas. In comparison to the volume of the gas or volume of the whole gaseous system, each and every structural unit, we call it as molecule, right? That molecule volume is almost neglected, right? We cannot consider that volume. It is negligible according to KTC. And another important postulate, that is kinetic energy of the gas molecule is directly proportional to absolute temperature. As temperature increases, kinetic energy of the molecules also increases. So as the temperature is increasing, that means more and more gas molecule starts to move. Whenever motion is there, that obviously kinetic energy is more, and the number of collisions also more. By that, pressure exerted by the gaseous system also increases. But remember that when our temperature remains constant, kinetic energy remains constant. There is no change in kinetic energy until and unless if we change the temperature. So that is also another postulate can be taken based on KTC. So these are the main postulates can be given for KTC. Based on the postulates of KTC, based on the postulates of KTC, based on the postulates of KTC, we have kinetic gas equation. We have kinetic gas equation. Children, kinetic gas equation is derived based on the postulates of KTZ only. And that kinetic gas equation can be given it as PV is equal to 1 by 3 mn u square, where this m is the mass of the gas. M is the mass of the gas, and this I can write it as even r 1 by 3 mn c square, either u or c. Anything can be taken, either u or c. If you take it that either u or c, it is taken it as a speed of gas molecule, speed of gas molecule. That is only we call it as RMS speed. Root means square velocity. So m is the mass of the gas and speed of the gas molecule, and n is the Avogadro number of Avogadro number for 1 mole of the substance. Then, but we know that this mass into Avogadro number, mass into Avogadro number can be taken as molar mass, because Avogadro number of molecules mass can be taken as molar mass only. Then PV is equal to 1 by 3. That molar mass I am indicating with capital M, that is U square. Of course, this U only can be written it as 3 PV upon M root over, or I can write it as U is equal to root over 3 RT by M, because you are aware of it. PV is equal to nRT. For suppose if N is 1 mole, 1 mole of ideal gas I have taken. If 1 mole of ideal gas is taken, then PV is equal to RT. That instead of PV, I have substituted RT. And this U can be taken it as RMS root mean square speed. Speed and velocity both are same according to chemistry. You don't apply physics here. In physics, speed and velocity are different. So PV is equal to 1 by 3 mu square can be taken, and this is RMS speed. RMS means root mean square speed. Of course, we will be discussing about molecular speeds. There are various types of the molecular speeds. No, that various types of molecular speeds also I'll be discussing about it. It's speed, not speed. Root mean not speeds. Root mean square speed. From this, you are going to calculate the kinetic energy. It's very important at mains level, especially calculation of kinetic energy. What we got it? PV is equal to 1 by 3 mu square, and this I can write it as PV is equal to 2 by 3 into 1 by 2 mu square. Do you agree? 2 gets cancelled. I'll get 1 by 3 only, right? So, but this one, if you notice it, it is this part half mu square is there, and this half mu square is nothing but what? Kinetic energy. So PV is equal to 2 upon 3 K, and that is the equation what we got it right. PV is equal to 2 upon 3 into K, or else I can write it as Ke is equal to 3 by 2 PV, and Ke is equal to 3 by 2. PV is nothing but what? RT. As you are aware of it, here I have given. Check it. PV is equal to RT, for N is equal to 1 mole, and that is the equation we have given it. So this Ke is equal to 3 by 2 RT. This is kinetic energy per mole of gas, because we have taken N is equal to 1 mole. N is equal to 1 mole here I have taken. Per mole of the gas, that is kinetic energy. Sometimes we call it as translational kinetic energy. This is called as translational kinetic energy. K is equal to 3 by 2 RT, we have got it. 1 mole in the sense for Avogadro number of molecules. Isn't it? Per mole of gas in the sense per Na molecules. For Na molecules, it will be 3 by 2 RT. And for one molecule, kinetic energy per molecule. If I take it kinetic energy per molecule, what do you write it? Ke is equal to 3 by 2 R upon Na. R upon Na into T. But this R upon Na, R is a constant. You are aware of it, you are familiar with it. Based on ideal gas equation, R is universal gas constant. Na is Avogadro number. Na is also constant. So I can write this R upon Na is another constant which is called as K. And this K is called as Boltzmann's constant. Just wait. This K is called as Boltzmann's constant. K is called as Boltzmann's constant. That's very important also, Boltzmann's constant. So this I can write it as Ke is equal to 3 by 2 Kt. But you are aware of it, 3 by 2 is a constant, K is a constant, and from this relation we can understand K is proportional to T. Kinetic energy is proportional to T. Kinetic gas equation, which gives us a better understanding about all the gas laws. All the gas laws are actually derived from the kinetic gas equation, and that proves all gas laws are following the kinetic gas equation. Means that gas is actually ideal gas, isn't it? And this K value, that is Boltzmann's constant value, can be given it as 1.38 into 10 raised to minus 23 joule Kelvin inverse molecule inverse, or I can write it as 1.38 into 10 raised to minus 16 erg Kelvin inverse molecule inverse. Molecule inverse, yes, because 1 joule is equal to 10 raised to 7 erg. So in erg you can express it as 1.38 into 10 power 16, and this value is very important. 1.38 into 10 raised to minus 23 joule Kelvin inverse molecule inverse, and erg Kelvin inverse molecule inverse value can be given directly, right? So it is all about kinetic gas equation and kinetic molecular theory of gases. In the next session, we will be continuing with another lecture of states of matter. Hope you like the video. Please subscribe to my channel and share it to your friends, as many as you can. Thank you. Signing off. We will catch up in the next video.